Hello, welcome to Chapter 7, Exponential and Logarithmic Functions. We're going to be doing Lesson 7.1, and in this section we're going to be dealing with exponential functions and how that refers to growth and decay. Alright, so what is an exponential function? Here's an example where we're using b as a parameter for the base of an exponent, and the variable is going to be the exponent. So the independent variable is actually what the exponent is. So for example, if I had f of x equals 2 to the x power, that just means 2 times 2 times 2 times 2 times 2. How many 2's I'm multiplying by? That's going to be represented by the x. So it could just be 2 to the first power, 2 to the second power, 2 to the third power. So what changes is the number of times you're going to multiply the base. If, for example, the base is 2. You can also have another one, we'll call it g of x. Maybe would be like, 0.5 to the x power. Or h of x could be 7 times 3 to the x power. So these are examples of exponential functions, and we'll go into the details in the next couple of videos. In this video, which is not an example from the book, I'm calling it the overview, just kind of an introduction to it, we're going to talk about what the exponential function means, and also how we write it and what things stand for. This base right here, the base of the exponent, is the number that's being repeatedly multiplied. Well, there's a couple things. First of all, the base has to be greater than 0, which means it has to be positive. Okay? Also, not only does it have to be positive, by which I mean, that it's not negative, but also we don't let the b equal 0. There's nothing wrong with the b equals 0. It's just, you just get 0. 0 to the third power just equals 0 times 0 times 0, which is 0. We get into a little bit of trickiness when we talk about 0 to the 0 power, but I'm going to push that off and let your calculus teacher in 2 or 3 years explain that to you. Okay? The other thing, and this is not wrong, but we just don't do it, we don't let b equal 1. So we don't have 1 to the x power. And that's just because it's trivial. 1 times 1 times 1 times 1 just means 1. So the only interesting things happen when b is greater than 1 and when b is between 0 and 1. Now, the cool part is that if b is bigger than 1, like for example the 2 here, if I get 2 times 2 times 2 times 2, the numbers get bigger. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Then if I keep doing that, I get 32, 64, 128, etc. And we'll be seeing more of those when I do the next example in this video. This is what we call exponential growth. So in the title of this, where it says growth and decay, that's the growth. If the base is bigger than 1. Easiest thing in the world. And when I graph a couple of examples in just a moment, we'll show you what the graph of exponential growth looks like. Okay, so b cannot be negative. We don't let it equal 1 because that's trivial. And if it's bigger than 1, then it becomes exponential growth. And I can actually kind of maybe I'll draw like a number line to kind of show you what I'm talking about. Okay, so here's 0, here's 1, and then these are negatives over here on this side. So we don't use these. We also don't use 0, so I'm going to put an open circle there, and we don't use 1. We can, but it's trivial. So when I said b is greater than 1, this is right here. And when I say 0 is less than b is less than 1, that's right here. Sometimes it's easier if you see what a picture is. So I'm going to use these numbers and these numbers. If it's bigger than 1, it's growth. What happens if it's between here and here? Okay, let's pick an easy one like 0.5 or 1/2. If I say half times 1/2, I get 1/4. If I divide it into again or multiply by 1/2, I get 1/8. These numbers So 1/4, 1/8, I'll put commas in them, 1/16, 1/32, etc. are getting smaller. Exponential growth, they get bigger. Exponential decay, they get smaller. So if I'm trying to decide if I have exponential growth or decay, I look at the base. If the base is bigger than 1, it's growth, and the graph is going to explode. I'll show you that in a minute. And if the base is less than 1, and it still has to be positive, so that's why we say between 0 and 1, then we have exponential decay. And both of these have very powerful applications in science and finances and other places. So this is like one of my favorite sections because it really ties in with a lot of different areas. All right, so let me do, I got 3 examples I want to do where I'm going to make a table and I'm going to draw a graph. I want you to watch this very carefully because you absolutely can use, one of these to figure this out. That's true. However, I really want you to know what's happening so that it's not just, I don't know, the magic answer box told me what to do. I want you to think about what's really happening. All right, so I have a table set up here. I did this in Desmos and I did a screenshot and then I printed it. So my first one, I'm gonna let my y value be what we just had, 2 to the x power. Now, I know I drew a vertical table. You can have it horizontal, except the x's would be on top and the y's would be on the bottom. That doesn't matter. I just did this because I need the space for the graph. Here's one thing that I notice every time whenever we start to make a table in either of my math classes, Algebra 1 or Algebra 2. People always want to start at the beginning. There is no beginning. There's no beginning here. It's an infinite number of x values. There's no start, there's no finish, there's no middle. It doesn't matter. So, it doesn't matter where you start. That's the first thing. But it does help if you pick the right number to start with. Okay? It doesn't matter, but it helps. And that number is 0. Because any number, 2 is in this example, raised to the 0 power equals 1. Except for 0 to the 0 power. And like I said, I'll let your calculus teacher talk about that later. So if I see this and I'm not multiplying by any coefficient, okay, that'll be one of the examples we'll get to in later videos, all right? So we're just going to start with b to the power of x. If I let x equal 0, then I get 2 to the 0 power equals 1. So that's a good place to start. And if I graph that, 0, 1, and I needed to make my scale really, really condensed here so I could go, otherwise if I drew like a normal graph, I wouldn't be able to show much of it. So I don't know if you can see the lines on the video, but this is 2, 4, 6, 8, 10. So 0, 1 is actually right here. I'll make a big fat dot so you can see it, even though it's probably too big. Okay, cool. That's a good place to start. So when we're graphing, always graph where x equals 0. And usually that's going to be y equals 1. Unless, of course, we got problems where then you're going to multiply it by something else. But hold that thought for just a moment. Now, the next easiest place to start is where x equals 1. 2 to the first power just means 2. And if I graph that, here's 1, 2, 3, 4, 5. And again, notice my scale is not the same on my x-axis as it is on my y-axis. So if it looks a little funny, that's why. Okay, I've done like a scaling issue to get it all in here. So when x equals 1, I get 2 to the first power. Maybe I'll write this. This is 2 to the 0 power, 2 to the first power. I get 2 to the first power, which is 2. So I come over 1 and go up 2. Now you're probably wondering why I have all this space here if I'm just down here. Don't worry, we'll figure it out. So when you graph also, you can also always graph where x equals 1. Those two are always going to be easy because any number to the 0 power equals 1, except for 0, and any number to the first power is just that number. You don't even have to do any math. Okay, it's easy, you just look at it. Now the rest of it, this one's kind of easy. They're not always going to be easy. We'll do examples as we go along. We may have to grab this guy, but this one we can do. If I say 2 to the second power, I know that that's 2 times 2, which equals 4. And if I do 2 to the third power, that's 8. And I can probably even stop this because look what I'm doing. I'm doing 1 times 2, 2 times 2, 4 times 2, 8 times 2 is 16, and 16 times 2 is 32. So let's graph these. I did 1, 2, now I'm going to do 2, 4. So I go 1, 2, and 2, 4 is right here. Still looks like I don't have a lot of space here. I don't need all this space is what I'm saying. 3, 8, 8 is right here. So again, I'm going by 2s. 2, 4, 6, 8. I went up 8. 4, 16. So here's 10, 12, 14, 16 right here. And this is really important that you see this also. From the x-axis to that dot is one space. From the x-axis to that point, I shouldn't have said dot, is 2 spaces. It doubled, and then it doubles again, and then it doubles again, and then it doubles again. This is a doubling function. You multiply everything by 2. Now, the next time, I'm up to 16. At 5, I should get 32. So I'm going to go 10, 20, 30, and 32 is right here. So look what's happening. It's starting to like curve upwards. I didn't put it on here, but let's see. 6 would be 64. 7 would be 128. 8 would be 256. 9 would be 512. And 10 is going to be 1024. Now, my graph only goes up to like, what, 52, 4, 6, not even 60. So my next one, 664, is going to be up here someplace. I can kind of estimate. I'm going to go off the graph, but maybe right about right here. So that's the positive numbers. There's a couple things I need to talk about. What about fractions? Can I have 2 to the 1/2 power? Is that somewhere between 0 and 1? Can I have 2 to the 3.7 power? These are good questions. And we're going to save that conversation later when we get to chapter 8, when we talk about, let me move that up a little bit for you, when we talk about rational exponents. But for now, I want you to think of this as being continuous. Continuous means no gaps, okay? You can draw it without lifting your pen, marker, whatever you're using. So I'm going to try to make a nice curve here. I'll go here, 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 and I'm heading up here some direction. And of course, no arrows. Don't forget that. And that's from IB, okay? So even though I kind of started off small for a couple steps, it exploded. It started to go up. That's called exponential growth. There's something about this side I want you to remember though, okay? This is never perfectly vertical. One thing I've seen students do is they want to all of a sudden make it go straight up. Don't. Think about this. Sorry, I didn't mean to put those two together. Don't, period. I want you to think about this. The x's are increasing. What are the x's? That's along this x-axis. So I'm still going, I'm going to put an arrow there. I'm not supposed to. I'm just doing this for demonstration purposes. I'm still going that direction. So my next x would be 7, which still goes over here, but now it goes way up to 128. And then I go x equals 8, which goes way up to 256. Now the powerful thing is that it's really, 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 really steep. I mean, you could probably ride a bike this far, but at this point you're going to fall over backwards. But it never, ever becomes perfectly vertical. So remember that, never perfectly vertical. Okay, so we got most of this graph. But notice I left out part of the table, and I might be missing some of the graph. What about 2 to the negative 1 power? All of these are going to be reciprocals. My iPad's in the way. Of these. So what's the reciprocal? And at 0 it's going to be okay, it's still going to be 1. But what's the reciprocal of 2? That's going to be 1/2. You can also say 0.5. What's the reciprocal of 4? 1/4. Reciprocal 1/8 would be 1/8, and this would be 1/16, and this would be 1/32. So what happens on the left side of the y-axis? Negative 1 gives me 1/2, and of course, because of my scale here, that looks like it's going to be right there. And then 1/4 is half the distance, and then 1/8 is even closer, and it's still getting closer. So now this part looks like this, and this is where the thickness of my Sharpie marker fails me, because this side never touches. Is there an S in there? No, sorry. Touches 0. So it never becomes 0, so it never touches the x-axis. If you do this on Desmos and you zoom in, there's always going to be a gap there. Every time, there's always going to be a gap there. It may not look like it if you zoom far enough away. I chose this graph in a way that I can draw enough of it this way, but I kind of fail here. If I zoomed in, and if I was doing electronically, not with this thick marker, then you can see that there's a little bit of a gap. And okay, so maybe the picture looks like it touches 0, but that's not what's happening. Look at the numbers. So the next one would be, and I'm going to just put them up here, 1/64 for when x equals -6. And then I get 1/128. And then I get 1/256, which are all the reciprocals of these. I get 1/512 and 1024. Those are never, ever going to get 0. And here's one more way to think about it. As I go bigger this way, and of course, I'm using a vertical graph, as my x's get bigger, my 2 to the x power is also getting bigger. Why? Because I'm just multiplying by 2. But as I go the other way, they get smaller. Why? Because I'm going the other direction, so I'm dividing by 2. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. 1/2 divided by 2, which is a half of a half, is 1/4. And I keep doing that forever. The only way I can multiply, and remember, dividing is just multiplying by the reciprocal, okay? But the only way I can multiply and get 0 is if I multiply by 0. And I'm never going to multiply by 0. I'm just going this way. I'm dividing by 2, which is multiplying by 1/2. That doesn't equal 0. So there's no way I'm ever going to get 0. And that's what's really cool, because I get closer and closer and closer and closer and closer and closer and closer forever, but I never touch the x-axis. Never, ever, ever. And if we were in class together, we'd have a real good conversation about this. All right. The next couple I'm going to do, I won't do as much explaining. Okay. For this one, I'm just going to pick a different base. I'm going to do y equals 5 to the x power. All right. So 5 to the 0 power, I'll write it over here. So this is what I'm thinking. Come on, marker. 5 to the 0 power. Remember, anything to the 0 power equals 1, except for 0. This is going to be 5 to the first power, which is 5. All right, so let me graph those two real quick. 0 gives 1, which is right here. Here's 2, 4, 6, 8. 1 gives 5. So I come over 1, and I go up to 5, which is right here. This is going to be 5 to the second power, which is 25. 25 times 5, or 5 to the third power, is 125. 125 times 5, which is 5 to the fourth power, excuse me, 625. And we'll do one more. I know I'm off my graph now. This is 3,125. So what can I graph here? 2 gives 25, which is right here. And 3 gives 125, which is way far up there someplace. So the only, and I don't even know where it would be headed. So this is going to look like this, and this is going to look like this. So keep in mind that even though it's really, 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 really steep, it's not perfectly vertical because my x's are still increasing, which means I'm still going to the right. Now what happens on the other side? These are the reciprocals of these numbers. So the reciprocal of 5 is 1 over 5. The reciprocal of 25 is 1 over 25. This is 1 over 125. Now, 1 over 3,125. Okay, I'm just going to grab my calculator just to show you what the decimal approximation of that. 1 divided by 3125. Now that gives it to me in scientific notation. That means that it is 0.00032. That is very, 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 very close to 0, but not equal to 0. And that's a major theme that we're going to be talking about. How close can you get to something without actually touching it? And spoiler alert, that's the entire premise of calculus. This massive math class that we have, that for most college curriculums covers 3, maybe even 4 semesters. For me, it was 3 semesters plus differential equations, which comes from calculus. Is all based on the idea, all of it. How close can you get to something without actually touching it? Mind-blowing. How do I draw it? I do my best. My marker is way thicker than I'm going to be able to have. So I have to kind of pretend. Remember, this is just a picture of the graph. Sorry, this is just a picture of the function. You know, it's kind of like if I drew a picture of a dog, it's not a real dog, okay? It's just a picture of a dog. So I try to like pretend that I have a little bit of a space in there. And obviously you can tell that it's probably a little bit closer than that, but that's like that. So you're probably wondering, okay, look. Am I supposed to draw it that close? Here's the deal, okay? Don't let the graph, I'll say it, cross the x-axis. On tests, in-person tests where I have students actually draw graphs, sometimes they'll just do this and they'll pass, they'll go below it. It's like, you weren't paying attention. Also want to show you something that happens. So this is a TI-84 graphing calculator. Let me show you what happens with this. I can do 5. This is the button. Looks like a roof, or we call it the caret button. Some people call it hat. I'm going to do 5 to the power of x. First, let me show you the table. Oh, sorry. Let me do something real quick. Okay. I'll do it again. I had some things in there set up differently. And I'm not going to redo the whole video just to make that change. First, let me show you the table. Okay, so these numbers are the numbers that I have. 1, 5, 25, 125. You can see them. And they go forever, because the x's can increase forever. And they get really, really big At 20, I've got 9 point something times 10 to the 13th power. That's 9 followed by 13 spaces. That's a big number. And if I go the other direction, here's 0, which gives me 1. 0.2 is the decimal form of 1 over 5. 0.04 is 1 over 25. And then they keep going. And then, where was I? At negative 5. There's my 3.2 times 10 to the negative fourth power. Okay, we got that. But let me show you the graph. This is why you don't use the TI-84 to cheat when you're drawing graphs, because the TI-84 does not have good resolution. Desmos is a little bit better. I cannot tell you how many times students draw from here to there. And when we do log functions in a couple of weeks, they do something else. And it's so very obvious that they're not doing it themselves, that they're using the graphing calculator. So the graphing calculator has its drawbacks. All right, let me do one more. I know this video's gotten long, but I think I'm getting all of the information out of the way that you need. We'll do one more real quick. So I'll make this easy. We already kind of know what this is going to be. Let's say y equals, I'll put it in parentheses, 1/2 to the x power. So again, 1/2 to the 0 power equals 1. And 1/2 to the first power is just going to be 1/2. If I do 1/2 times 1/2, which is 1/2 to the second power, I get 1/4. And then to the third power is 1 over 8. To the fourth power is 1 over 16. These numbers look familiar. 1 over 32. So what does that look like for the graph? 0, 1 is right here, and then 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 here. Well, that doesn't, I don't know, that's kind of confusing. Wait a second, maybe I should do more. What did I say the negative exponents were to the positive exponents? They are reciprocals. So what's the reciprocal of 1 over 2? 2. What's the reciprocal of 1/4? 4. The reciprocal of 1/8? 8. This would be 16, and this would be 32. So when x equals -1, y equals 2. When x equals -2, y equals 4. And then 3 gives me 8. And then 4 gives me 16. And then 5 gives me 32, which is right here. So if I draw this graph, so I'm going to curve this like this. Now it's getting really steep, but never vertical. And on the other side, try to draw it a little accurately. It looks like I'm touching, but I'm not. It never equals 0, which is another way of saying never touches or crosses the x-axis. And right here, 1/2 to the 0 power equals 1. And right here, 1/2, whoops, sorry, not there, excuse me. Well, that's 1/2 to the -1 power, which equals 2. But that's the one I was talking about. 1/2 to the first power equals 1/2. So we know where we can start near the x-axis. We can figure out a couple. We can figure out a couple going both directions. But after a while, you're not going to be able to draw it any further, because this side's not going to be, it's going to go down forever, but it's never going to touch the x-axis. This side is going to go up forever, but it's never going to be perfectly vertical. Okay, we got that. You're probably looking at this going, man, that looks familiar. Let's go back to this one. These numbers here were these, and these here were those. So they like flipped. This is an example of exponential growth. As I go to the right, where the x's are bigger, the graph goes up. This is an example of exponential decay. As I go to the right, where x equals bigger, the graph goes down. And exponential decay has lots of examples. Later in chapter 7, we will talk about half-life and how we know when Tyrannosaurus rexes were running around. Okay, that's an extra long video. I know, I'm sorry, but this is just a way to get out most of the information. I'll try to make the next videos a little bit shorter.